Okay, so for our first class, we are going to look at our continuous rotation servos. In our previous class, what was a microcontroller? We looked at the standard servo, and with the standard servo, we sent it a pulse, and the servo would go to a certain position and would hold that position. Now, the continuous rotation servo works a little differently. When we send it a pulse, that's going to tell it a direction, and the servo is going to turn in that direction for a certain amount of time. So yeah, you got to make sure if you have your old servo from the old kit that you don't use the wrong servo. It'll say here right underneath Parallax, it'll say continuous rotation. So you can just look right at the top of the servo to make sure that you're using the right one. So a little review basics on the servo. There's a connecting horn piece on the top. See where these four spokes with little holes through them. That's called the horn, and you can connect things to it like a wheel or a propeller or whatnot, or a rudder, and they'll move with the servo. The servo itself is this rectangular or cube box on the bottom. And then there's this 3-lead cable that comes out here with a 3-pin connector there. The high and low signals you'll program the basic stamp to send to the servo motors must last for a very precise amount of time. That's because the servo motors measure the amount of time the signal stays high and use it as an instruction for where to turn. For accurate servo motor control, the time these signals stay high must be much more precise than you can get with a high and a pause command. You can only change the pause command's duration argument by 1 millisecond. Remember, that's 1,000th of a second at a time. There's a different command called pulse out that can deliver high signals for precise amounts of time. These amounts of time are values you use in the duration argument, and they are measured in units of 2 millionths of a second. Okay, so the pulse out command takes a pin and a duration argument, and the duration argument is in units of 2 microseconds, or 2 millionths of a second. A microsecond is a millionth of a second. It's abbreviated µs. Be careful when you write this value. It's not the letter U from our alphabet. It's the Greek letter mu. For example, 8 microseconds is abbreviated 8 µs. You can send a high signal that turns the P13 LED on for 2 µs. That's 2 millionths of a second by using this command, pulse out, pin 13, 1. This command would turn on the LED for 4 microseconds, pulse out 13, 2. That's because it's 2 times 2 microseconds is 4 microseconds. This command sends the highest signal that you can actually view. It does a pulse out 13 for 65,000. How long does that LED connected to pin 13 stay on when you use this pulse? Let's figure it out. It's 65,000 times 2 microseconds, which is 13 milliseconds, or 0.13 seconds, which is still pretty fast, 1300ths of a second. This is kind of an interesting point. A very long duration for the microcontroller is something that looks like just a very quick flash to us as humans. So what we found is that human beings can see things that are maybe coming in at around 50 to 100 times a second. Old movies used to be 30 frames per second or 30 pictures per second. and people thought that was pretty good. So relative to our thinking, we can usually think about something that is just a quick flash as being maybe happening 100 times a second. But for microcontrollers and computers in general, they can work on a completely different time level. A thousandth of a second is absolutely nothing to them, never mind more like a millionth or even a billionth of a second now. Okay, so we're going to connect the servos to our boards here. Now, the problem we have is with the newer kits that a couple of us have in class, they're a different board type. So there's going to be two different ways that the servos are actually going to be hooked up in class, depending on which board you have. If you were in class last semester, you should have the homework board, and if you're joining us this semester, you should have the Board of Education board. So I'm just going to go through connecting it up on the Board of Education now, so that'll be pertinent to the new packages, to the newcomers, and then I'll quickly go over the homework board as well. So yeah, for the Board of Education, we're going to start by powering it off. There's a switch with actually 3 settings here. Make sure that setting is all the way towards 0 or all the way to the left to power it off. There's a quick note here about using the right batteries. I'm going to supply the batteries, so it shouldn't be a problem, but they're basically saying don't use rechargeable batteries. Use full 1.5 volt batteries. There's also another note about using different DC or AC power supplies, but we're not doing that. We're going to use the batteries. Okay, so this arrow here in figure 212 is showing us that there's a little jumper on our board in between the 2 connection points for the servo. And that jumper can be set to either VDD or VNN, or VIN, sorry. And it says select VIN if you're using the battery pack that comes with the Bobot kit. And we are going to do that. So that's our kit, and that's what we're going to do. So make sure that on your board it's on VN and not VDD. And as you can see, the 2 3-pin headers just plug right into these ports here. This port's actually labeled X5 right there. And you'll know from the top, there's a label on the top. This one's 12, corresponding with pin 12 here. And this one over here is 13. I busted that. There's 13, as in 13. Alright, so it should look this on your bench or your desk. So you'll have the 2 servos. They'll be connected to the ports kind of on this side of the board there. You'll have the battery pack on the Board of Education kit. It will have this coaxial connector that plugs right into the board. So once you got that hooked up, and there will actually be USB here, not a serial cable. That's an old serial cable, so it won't look like that. It'll look a little different. Okay, so once you have the servos hooked up, we're going to add in our LEDs. So it's calling for the 470 ohm resistor, and then the LED, of course, on pin 13, and then another set of that on pin 12, another 470, and an LED, and then eventually goes into ground. So right, so here is our pin 13, And the resistor here, it is the yellow, violet, brown resistors. And then the LED right here. So remember the shorter leg or the side that is flattened goes into the ground, the VSS. That's the cathode side, the negative side. And then they actually show a little plus here. The plus goes in the same row as your resistor in the prototyping ports. All right, so this part here, this is for people who had the class last time or people who have the homework board. So, all right, so this we're going to have this slightly modified battery pack in ours where it doesn't have that BNC connector. It's been stripped and tinned, and there's going to be two 3-pin headers that we have to put on top of the board, the prototyping area, so that our 3-pin connectors can sit into the prototyping area. All right, and then we'll need a couple of jumper wires and then our 4 batteries. All right, so on the schematic diagram here, they're calling out the battery pack power separately. Oh, there we go. So just note that that's coming directly from the battery pack and not from the board. This is that note here. VPB stands for voltage battery pack. Same notes about the recharge. Okay, so they do a little trick here on the board, so I'll just point it out. When you put down your 3-pin headers, there's an overlap on this pin here. So the 3rd pin on the top one and the 1st pin on the bottom one, they go in the same row of ports on the I/O prototyping area. They overlap, and they're both going to be used for this VSS, which is the ground. That's called a common ground. And so a lot of things will tie in to VSS. You can see these 2 wires here. The other side of our battery pack will actually be tied into ground as well. And in fact, there's actually a big copper plane in the board called the ground plane, and that's also tied to ground. I will note here that this white and black stripe wire here coming from the battery pack, that is the VPD supply, the power from the battery pack. And notice it comes in on that row there, which is the middle row of the top 3-pin connector. And then if you can see, there's a red jumper that goes to the middle row of the bottom 3-pin connector. And so the middle of those connectors, both those connectors, is this red wire. The red signifying a hot, that's the voltage for the servos. So be careful when you put that on. Make sure it doesn't get crossed with ground. Remember the grounds are done by overlapping the 2 3-pin headers. And also I should point out that the top 3-pin header is set up with the white on the top, and then the bottom one is set up with the white on the bottom. So they're actually swapped in the direction that they go. And because they both have black on the one side, the blacks are joined in the middle, and that's how they get the blacks common. Now black typically stands for ground, by the way, and that's why you see these VSS, ground meaning VSS or the negative side of the battery. You see these black wires coming into VSS because black typically stands for the ground, and the red usually stands for the plus side, the positive side of the battery, or what they call the hot side. And in this case, the white is our control signals, and those are the signals that are hooked up to our I/O pins that we're going to control the servos with our microcontroller. Oh, and there's also a note here on making sure to disconnect both batteries from the homework board. So you got to do the 4AA pack, the battery pack, and you have to do the 9 volts as well. Okay, so now from here on out, this is common amongst both boards. So the first activity is going to be to center the servos. So when we get our servos, they may be centered fine, but we have to check. This is sometimes called calibration. So what we're going to do is we're going to send the servo a pulse that tells it to hold the position that it's currently in. And if it doesn't hold that position, if it starts to turn one way or another, that means we have to adjust or recalibrate the servo so that it's centered. So we tell it to hold the position by sending a 1.5 millisecond pulse width. Okay, and in order for it to maintain that for a while, we got to keep sending these 1.5 millisecond pulse widths over and over again. As you can see, there's another one here. Okay, so there's another 1.5 millisecond pulse width over here, and notice that it's spaced by this 20 millisecond pause, or a 20 millisecond delay in between. So that's just their specification, that you send it a pulse width and then you wait 20 milliseconds. And we really have to send these over and over again in order to achieve the effect that we want. So, right, so how do we send these pulse widths? We want a 1.5 milliseconds or 1.5 thousandths of a second width. So the duration of the pulse width command is in units of 2 microseconds, or 2 millionths of a second. So basically, we just got to divide our duration by that 2 mic. So we take our 1.5 milliseconds here, divide it by 2 millionths of a second, and that gives us 750. And you can think of that as, oh, well, if I just double 750, because this is 750 in 2 microsecond intervals, then you'll get the number of milliseconds. So 750 plus 750 is 1500 microseconds. So 1500 microseconds is 1.5 milliseconds, which is what we're looking for. But don't worry about the math. You'll see that we're just going to get a few different ranges of values to program in, and it's not a big deal. You don't have to worry about dividing by these thousandths and millionths things. Alright, so from that, basically we know that the pulse out command of 750 is going to give us a 1.5 millisecond pulse, and that's going to tell the servo to center itself, or to hold that position. Okay, so a note on Board of Education users, that's the new kit. When you turn the power on, make sure that it is in position 2. and position 2 is going to send power to those server ports on that board. For the homework board, users were manually putting the power on, so just make sure that the battery pack's plugged in. Okay, so we're gonna put this program in, and we're gonna run it on our board connected to, this is only for the servo in port 12. And then if it starts to move, then it's out of calibration, needs to be calibrated. So what you do is you just gently stick in the screwdriver into the port in the back of the servo, and you just gently turn the screw left or right until the servo stops turning, and then it's calibrated. So this loop's going to run forever, so it should either keep turning or stop turning once we have it correct. And then basically we're going to come back and we're going to do that same exercise with the second servo to make sure that it is also calibrated and centered. Okay, new section here, how to store values and count. Okay, so this section just goes over variables and how to use them. So variables are memory areas that you can give a name to or a label. So you declare a variable in this pbasic with the key var, and then you give it a name and a size. So the name actually goes first and the size comes later. And then these are the types of sizes and what kind of values that they can store. So you can either have a bit, a nibble, a byte, or a word. Okay, a bit can only store a 0 or a 1. A nibble can store the values 0 to 15. A byte can store the values 0 to 255. And a word can do 0 to 65,000 or negative 32,000 to positive 32,000. So again, in order to declare a variable, you give it its name, you give that keyword var, and then its size, like value var word, and another value var word. So that declared two variables. Alright, after you declared your variables, you can initialize them or set them to a value. So you do that with the equals operator. So you say value equals 500 or another value equals 2000. Alright, this note here just says by default they're set to 0, so you don't have to necessarily initialize them. Okay, and then here's a couple of examples. This the asterisk or star down here, that that thing means multiplication. So when you see, value equals 10 asterisk value, that's going to say make value equal to the value times 10. So if we started it out with 500, it will now be 10 times more, so that would be 5,000. And so this is the idea, right? With variables, the values can vary. So what was 500 is now 1,000, but it still has the same name. Okay, it's just the contents of the memory have changed. All right, and here's another example. Another value can be set to 2 times value. So if value was we said 5,000, then this would be 10,000. Here's a sample program that just goes over some of that. So we'll do that in class, as well as calibrate the servos in class. Okay, when you see debug with this question mark operator, that means it expects a variable afterwards, and then it's going to print out the value of that variable. It might actually print the name and the value. I can't remember. Okay, so one great use for these variables is to control how many times we iterate through a loop, or how many times we do commands for a loop. So they introduce a new loop here, the for next loop. So for next, we can give it a start value and say 2, and then give it an end value and a step. And then it'll do any commands between the for and next. So let's just kind of look at that down here. So they declare a variable here, my counter, and it's of size word, so it can take 0 to 65,000. And how they use that variable is they say we want a loop that runs 10 times. So they say, all right, well, we'll run count the value in variable my counter from 1 to 10. So it says before we start the loop, set it to 1, and then run it until the value is 10. And then because we didn't specify a step, it automatically increments it every time that the loop is ended. So this loop would run 10 times. And notice we have the debug here that prints out the variable that's used as the iterator for the loop. So that's going to print out the numbers 1 through 10. So yeah, you guys should check out that for next programming class. We'll probably be using that for next construct quite a bit in class. These are just some more examples. Again, when there's no step value given here, it just means step of 1. Here's an example where it does a step of 3. So that's going to skip and count by 3s. And this is kind of an interesting one. It actually is going to go from 21 down to 9. So it's going to count down. So 21, 18, 15, 12, 9. Yeah, this note up here, it talks about testing individual components or subsystem testing, and it's a really valid point. You need to test just one little part of the unit because the entire thing can be pretty complex. So it's a really good idea to test and make sure that the component you're working on or you're adding currently really actually works, rather than try and build something all at once and then not be able to figure out what is wrong. So we're going to test out our servos here and make sure they are working properly, or that we can get them to work properly. Okay, so we want to make the continuous servo turn counterclockwise. So in order to do that, we want to send it a 1.3 millisecond pulse. So yeah, you can see the pulse here, and notice that it shows the servo turning clockwise here. So right, so and then we need to do the 20 milliseconds in between the pulses of 1.3 milliseconds. So last time our pulse was 750 to center it, and that was a 1.5 millisecond. In order to do a 1.3, we got to do this 650. Duration of 650. So we'll do that on one of the servos, make sure it's right, and then do it on the other servo. And then similarly, we'll do a 1.7 millisecond pulse width here, and we should see the servos go counterclockwise in this direction. So it's the same type setup. We still have the 20 millisecond delay in between our pulse. It's just that we changed the pulse width to mean something different. So the larger number, the 1.7 milliseconds, is going to tell it go counterclockwise. And let's see, that's 850. So we'll test that out, make sure that we can do stop clockwise and counterclockwise. Here's a note on pulse width modulation. A voltage that spends certain amounts of time in two different states can be considered as a series of resulting states and a pulse. Here's a list of different pulse signals that control your servo speed and direction. So yeah, they say 1.5 makes the servo hold still. That's what we use to center it, but it can also be used as a brake. 1.3 milliseconds tells it to turn clockwise. Okay, 1.7 milliseconds tells it to turn counterclockwise. Alright, these signals send brief amounts of time at high level pulses that are separated by low signals or resting states. The program can adjust the pulse duration, which is the amount of time that the signal is high. This duration is commonly called the pulse width because the amount of time the signal is high looks wider or narrower in the timing diagram or in the device on an oscilloscope that plots voltage against time. Modulation is the process of adjusting a property of a signal that is being transmitted to make it convey a certain information. With a servo, the property that is modulated by the pulse width is the amount of time the signal is high. The information it conveys to the servo is speed and direction. The servo control signals are examples of positive pulses with low resting states and high active states. Negative pulses would be inverted version of the high resting states and low active states. Okay, so this program here, you can see it does an 850 and a 650, so that's going to be clockwise for one and counterclockwise for the other, meaning the one on pin 13 and the one on pin 12. Okay, so and the other thing they want you to do is try and figure out how these things work, give a description and its behavior. So that's stuff we can play around with in class, can try these different commands. Okay, here's some examples of using that for next construct in order to get the servo to move in a direction for a certain amount of time. So they go through 100 iterations here, and they say that's going to let the servo turn for a few seconds. Okay, so if we can get through most of that, we don't have to get through all that in class, but if we can get through some of that in the first class, that would be really good. Don't worry if you don't get all of this done in the first class. A lot of it will just be going over again in the next class once we get the servos hooked up onto our robot. In the next class, we'll be building the chassis for our robot and putting the servos on it. So once we've done that, we're going to go back through the process of calibrating these servos again and testing them out for clockwise and counterclockwise. So don't worry if you don't get through the whole thing in the first class.